everyone and welcome to CEC eGurukul live lectures. You are watching the 11th lecture in the series Mathematical Methods for Economics, and I'm your instructor Neeti Bhutani from Hindu College, University of Delhi. Today I will not start a new topic, but we will go over some economic applications of some of the concepts that we have covered so far in the lecture series. In fact, I'll take up two economic applications from the topic quadratic functions, which I covered in one of my earlier lectures a few weeks ago. I also have a very interesting economic application where the discussion will revolve around the concept of a circle. In fact, you must pay close attention here because this application uses a trick which is typically used in a course like game theory. And if you have an inclination towards studying a course like game theory in your bachelor's course, I think you'll find this economic application useful. Finally, if we have time, we will do some light, fun problems of a general nature towards the end. But first, let's get started with our economic applications relating to quadratic functions initially. But even before that, just to make sure that we are all on the same page, let me do a quick recap of quadratic functions before starting. This will just be about 3 to 4 slides. Okay. A general quadratic function, if you look at the slide here, is of the form f of x equal to a times x square plus b times x plus c, where a, b and c are constants. And it just might be helpful for you to remember for the slides that will just come that a is a coefficient of x square, b is a coefficient of x, and c is the constant by itself. Here we also impose a restriction that the constant a is not equal to 0, because if a is equal to 0, then you'll see here that the first term will vanish and our function will become bx plus c, which is a linear function. So because we don't want a linear function here, we're talking of quadratic functions, so we are going to impose the restriction that a is not equal to 0. Now, you have, if you have followed my earlier lecture titled Quadratic Functions, we had talked about the process of completing the squares in that lecture. And if we follow the process of completing the squares, this function that you see on the slide here can alternatively be expressed as a times x plus b by 2a the whole square minus b square minus 4ac divided by the whole thing divided by 4a. You can check this result out by completing the squares right now itself, or you can go back to my earlier lecture titled Quadratic Functions, or you can just for the time being take this result, just trust me for what I have here, and take this functional form as given. Now here we have the result. Once we obtain this functional form for the quadratic function, we have the result that when a is negative, when a is less than 0, or when the coefficient of x square is less than 0, the function f of x attains its maximum at the point x equal to minus b upon 2a. Now, if you remember, quadratic functions are represented graphically by a parabola. So, when a is negative, here in terms of a graph, you would typically have a parabola which is facing downwards, and therefore it will have a maximum which will then be at x equal to minus b by 2a. And when a is positive, when the coefficient of x square is positive, the function f of x attains its minimum at the point x equal to minus b by 2a. So let's get a visual sense of things here for the cases where a is negative and where a is positive. So when a is negative, you have a parabola that faces downwards, and clearly you can see here on this slide where my cursor is pointing, this parabola has a max at x equal to minus b upon 2a. And just to keep this formula straight, it's basically minus b, which is the coefficient of x, divided by 2 times a, which is 2 times the coefficient of x square. And when A is positive, we have a parabola that faces upwards, and clearly you can see that this kind of a parabola has a min at x equal to minus b upon 2a. Now, if you notice here, the expression for the maximum point or the minimum point is the same for both the parts of the result, whether A is negative or A is positive. The only difference here is that when A is negative, you'll have a max at x equal to minus b by 2a, whereas if A is positive, you have a min. Now, the next question one can ask here is, we've located the maximum and minimum points, but what is the value of the function at this point x equal to minus b by 2a? What is the value of the function at the maximum point or the minimum point? And for that, you can see that because the function f of x is expressed as a times x plus b by 2a the whole square minus of b square minus 4ac divided by 4a, when I put x equal to minus b by 2a in this expression, if you see where my cursor is pointing, then you see that automatically I'll get the first term in this expression will get cancelled, the x plus b by 2a will get cancelled, and I'll get the value of the function at minus b by 2a, which is nothing but minus of b square minus 4ac divided by 4a. So let me quickly summarize the result that I have talked about so far for quadratic functions. If a, the coefficient of x square, is negative, then the function f of x equal to ax square plus bx plus c has a maximum at x equal to minus b by 2a, with the maximum value of the function being minus of b square minus 4ac divided by 4a. And similarly, when a is positive, the function has a minimum at x equal to minus b upon 2a, with the minimum value now being minus of b square minus 4ac divided by 4a. So with this as a basis, we'll now start talking about maximization and minimization problems, or optimization problems as they are called in economics. But before we get started, let's get some sense. Let's try and make some sense of this word optimization. The question is, what exactly do we mean by optimization, or what does it mean to optimize? So the way to think about optimization is, let's suppose you have a goal. Then if you're optimizing, you're basically asking yourself, what is the best way to achieve that goal? Now, for example, your goal as a student may be to be the topper of your class at the end of this year, the academic year. And for this, you might want to ask yourself, okay, how many hours should I put in during a day? How many hours of effort should I put in during the day so as to achieve my goal of becoming a topper? Now, clearly, there might be constraints in the way you have at most 24 hours in a day, and you may not just want to be studying all the time. There are also other things that you have to do, or you may not be equally efficient studying for so many hours. So you have to optimize here, and you have to make your best possible choice of the number of hours to study. So the point that I'm trying to make here is that you have a goal, and at the same time there may be constraints that you face while achieving your goal. But the whole idea of optimization is, you ask yourself, what is the best way to achieve that goal? What is the best choice, or what are the best choices that I can make to achieve my goal? So the key phrase here is best choice or best choices. That is what we talk about in optimization. Right, so let's look at our first example, which is an example borrowed from the textbook that we are using for this course. It's a textbook by Sitzsater and Hammond. I've adapted it just a little bit because I wanted to ensure a particular flow of the discussion here. So anyways, the story goes like this. Let's suppose there is a single firm in the market, and this firm is the only seller of the commodity that it produces. In economics, we say whenever there's only one firm and it's the only seller of the commodity it produces, we say that such a firm enjoys a monopoly in the market. Let us assume that the total costs of this firm are represented by the variable C, where you can see my cursor is pointing now. So this C represents the total cost function, which is given by the quadratic function alpha q plus beta q square. Here alpha and beta are parameters which are both positive, and q here represents the level of output. Because q, as you know, cannot be negative, output cannot be negative, we have the restriction here that q is greater than or equal to 0. Further, let's assume that the price at which the firm can sell its output is given by the inverse demand function P equal to A minus B times Q. Now this is known as the inverse demand function because we have here price on the left hand side, which is a function of quantity. Had it been the other way around, where the q term was on the left hand side, so in this case q would become q equal to a minus p divided by b if you solve for q. So if you were to express q as a function of p, quantity as a function of price, then that is something we would call the direct demand function, because you're directly determining q as a function of price. So anyway, the point here is that the monopolist produces a particular level of output, and assuming that whatever is produced is sold, that will be sold at a price which is determined by this inverse demand function P equal to A minus BQ. And needless to say, here A is positive and B here is also positive, because as you as you would know by now in a course like micro, if you've studied micro, the demand curve is downward sloping. The inverse demand function here is downward sloping. So because you already have a negative sign in front of B, so B has to be positive to ensure the negative slope. Now let us assume further that the objective of our monopolist is to maximize profits. The expression for profit, first of all, profit here is represented by the symbol pi in mathematics, in economics in particular, and the expression for profit is pi of q equal to total revenue minus total cost. Total revenue represented by capital R and total cost represented by capital C. So profits equal the difference between total revenue and total cost. Now what is total revenue? Total revenue is what the firm would receive from the sale of its output. Now if P is the per unit price, which is A minus BQ, and there are Q units of the output which are sold, then the total revenue for this firm would be mathematically given by R equal to P times Q, which is then equal to A minus BQ times Q. Right, and you already know the expression for the cost function, which is C equal to alpha q plus beta q square. So now we can calculate the profit, the expression for profits for this monopolist firm, and that is nothing but total revenue minus total cost. So that then, please see where my cursor is now. So total revenue is A minus B times Q, the whole thing times Q, minus the total cost, which is then going to be alpha Q minus beta Q square. Now let's collect the terms containing Q and Q square respectively. So if I collect the terms containing Q, I have A minus alpha times Q minus of B plus beta times Q square. And here you can see clearly that your profit function pi of Q, it is a function of Q first of all, and this is also a quadratic function. So we are now all set to maximize profits for this monopolist, and as I just said, the monopolist maximizes his profits, and he does so in such a way by choosing Q. The Q is a variable that he chooses. So his optimization problem is written like this, where the monopolist chooses Q to maximize pi of Q, which represents profit. Q here is also known as the choice variable, because this is what the monopolist chooses. This is his choice variable. This is a variable that he can manipulate. He can't manipulate the other terms here. If you look here, the other variables here, the parameters are A, alpha, B and beta. These are parameters which the monopolist can't manipulate here. He is going to be choosing Q so as to maximize profits. Another way to read this expression, which I have here on this slide, which is shaded in yellow or orange maybe. So you can also read this expression as maximize, the monopolist maximizes pi, which is profit, with respect to Q. So these are the alternative ways in which economists talk about reading an optimization problem. Okay, now let's get started with the actual optimization process. Our optimization problem is one where the monopolist maximizes pi with respect to Q. He chooses Q to maximize profits. And profits, as we know, as we just found out, the expression for profit is given here by A minus alpha times Q minus of B plus beta times Q square. Now, if you remember what I just told you in one of the earlier slides just a couple of minutes ago, that if the coefficient of Q squared is negative here, then we're going to have a maximum for this function. And clearly you can see minus of B plus beta here is negative. So this function pi of Q will have a maximum at minus of, we'll have to take the coefficient of Q first. So this is the formula I'm using. I've just changed the notation a little bit because there was some overlap with my objective function here. Objective function here is pi of Q. So if I have the function denoted by A bar x square plus B bar x plus C bar, then if A bar is negative, the max occurs at minus B bar upon 2A bar, where B bar is in this case going to be the coefficient of Q, which is A minus alpha. So put that here for B bar, and for 2A bar I put 2 times minus of B plus beta, which then gives me A minus alpha upon 2 times B plus beta, and that is then our monopolist firm's optimal quantity, the quantity that he chooses to produce and sell at the optimum. The question now is, what are the firm's profits at the optimum? So the firm's profits at the optimum can be calculated by using this expression here, minus of B bar square minus 4A bar C bar divided by 4A bar, or alternatively you could simply just substitute the optimal quantity Qm into the monopolist's objective function, which is this. Objective function is nothing but it's a function that you're maximizing or minimizing, and in this case our objective function is the profit function itself. So when you substitute Qm instead of Q here, we get the optimal level of profits, the maximum profits at the optimum. So that would be given by A minus alpha times Qm, which is A minus alpha divided by 2 times B plus beta minus of B plus beta times A minus alpha by 2 times B plus beta, the whole square, because that's a Q square. And when you simplify this, you're going to get A minus alpha, the whole square, divided by 2 times B plus beta minus A minus alpha, the whole square. And you can see one of the B plus beta terms will get cancelled here. So in the denominator here in the second term, you'll have 4 times B plus beta. Now when you solve, just take the common LCM, and then you'll get 2 A minus alpha the whole square minus A minus alpha the whole square, and a final result for profits at the optimum would be A minus alpha the whole square divided by 4 times B plus beta. So let's summarize our result. If the objective function is what is given here on this slide, then the monopolist maximizes his profits at Qm equal to A minus alpha divided by 2 times B plus beta, with the profits being A minus alpha the whole square divided by 4 times B plus beta at the optimum. Now note here that this result is valid if A is greater than alpha, because you can see here if A is less than alpha, what will happen to our Qm? Our Qm will become negative. If A is less than alpha, then Qm will become negative, and because output can't be negative, we'll have the result that if A is less than or equal to alpha, the firm will not produce at all. So that Qm, which is the quantity produced at the optimum, that will be 0, and if Qm is 0, you can see here in the objective function, if you put Q equal to 0, your profits will also become 0. This can also be shown graphically. I've shown the two cases where A is greater than alpha and A is less than or equal to alpha. so you can get a visual sense of things. The first case here that I'm showing is one where A is greater than alpha. Here the profit function looks something like the blue curve here. First of all, it has to pass through the origin, because if Q is 0, profits are 0. And because A is greater than alpha, the maxima occurs on the positive side of the quantity axis. So that's going to be somewhere here. So in this picture, it's this point here, which represents A minus alpha upon 2 times B plus beta. However, if A is less than or equal to alpha, you can clearly see here that your profit function will end up being something like this, where the maxima is occurring on the negative side of the quantity axis. And clearly, because this firm can't choose a negative level of output, it's going to choose Q equal to 0 at the optimum. Now, if you look closely at this graph, you'll notice that the firm can't even choose any positive level of quantity, because if you see where my cursor is right now, if it chooses any positive level of quantity, then what will happen? The profits will become negative. So the best that this firm can do here is that it should just not produce anything, so that the profits at the optimum are simply 0. Now we're going to have a little bit of a variation. Let's bring in a little twist to this problem. So our initial problem was maximize pi of q with respect to q, where pi of q is given by a minus alpha times q minus b of b plus beta times q square. Let's assume that in the inverse demand function p equal to a minus bq, the price is now given as A. That is to say, B is equal to 0. So if you assume that B is equal to 0, then the price that the firm receives is equal to A, which is to say that the price is given to the firm now. It can sell all it wants at this going price, which is P equal to A, but it cannot influence the price by its production or production activity. And such a firm that takes the price as given is known as a perfectly competitive firm in economics. So we have introduced 2 kinds of market structures for you today. In case you haven't done any microeconomics, I have attempted to make you familiar with the term monopoly, where you have a single seller in the market, and here and I've also introduced the term perfectly competitive firm for you, where the firm takes the price as given. It is P equal to A. Now here, if B is equal to 0, our problem will become maximize A minus alpha times Q minus beta times Q square, because B has become 0 in the original objective function. So with this as the new objective function, let's see what our optimization exercise will give us. Again, if you notice, the coefficient of Q squared, so again this profit function is a quadratic function, and the coefficient of Q square is minus beta, which is negative. So clearly this function pi of q is going to have a max, and where will it have its max? It's going to have its max at minus of, if you remember the formula, you have to first take the coefficient of q in the numerator, which is a minus alpha, and in the denominator you will take 2 times the coefficient of q square, which is minus beta, and once you just cancel out the negative signs, you will get the optimal quantity chosen by a perfectly competitive firm, which is a minus alpha divided by twice beta. And once you substitute this optimal quantity into the firm's objective function, you will get pi c, which is the level of profit at the optimum. That is going to be equal to a minus alpha times a minus alpha upon 2 beta, because that's our q now, minus beta times a minus alpha by 2 beta, the whole square, which you can simplify, and you'll see that you'll get the expression a minus alpha the whole square divided by 4 beta. Again, you have to remember that this result will also be valid if A is greater than alpha. And just to give you an alternative perspective to the problem, here we have a situation where the original problem was maximize pi of q with respect to q, where pi of q is given by a minus alpha times q minus of b plus beta times q square. Okay, so the function here we found for the monopolist that the function has a maximum at Qm equal to a minus alpha upon 2 times b plus beta, with the profits at the optimum being a minus alpha the whole square divided by 4 times b plus beta. So again, provided that a is greater than alpha. Now what we can do is, once we have this result for the monopolist, and suppose we want the result for the perfectly competitive firm, in this result itself also you can put b equal to 0, so that when you put b equal to 0, you will get the optimal quantity that will be chosen by a perfectly competitive firm, which will be a minus alpha divided by 2 beta, and this is exactly the result that we had obtained in the previous slide, with the optimal profits at the optimum being a minus alpha the whole square divided by 4 beta, again the same result that we had earlier. Okay, and just as an aside, let me just give you some sense of our cost function. We have taken this particular kind of cost function, which is quadratic, and you can see here there are no fixed costs. So let's just get a sense of what this cost function looks like. So our cost function here is alpha times q plus beta times q square, and here you can see beta, the coefficient of q square, is positive. So this is a cost function which will actually have a minima at q equal to, again use the formula that I told you in one of the earlier slides, minus of the coefficient of q, which is alpha, divided by 2 times the coefficient of q square, which is beta, which is, so that is to say that the cost function achieves its minima at minus alpha divided by 2 beta, which you can see is less than 0 because both alpha and beta here are negative. So pictorially this would give me something like this, a graph like this, a parabola like this, which you see on the slide here, which will pass through the origin, because if q is 0, you can see c is also equal to 0, and here the minima is on the negative side of the quantity axis. Now because quantity, again we said output can't be negative, here we'll have a situation that the relevant portion of your cost function would just be this blue part of the parabola, which is shown in bold. So I have separated out the two parts of the parabola. One is, so till the origin this parabola is dashed. So that part will not concern us because that involves a negative output. But this part, which is on the positive side of the non-negative side of the quantity axis, that's going to be the relevant portion of the cost function. Okay, so that was our first example, and I hope you've been able to understand it, and I hope there's been some value added also for you in terms of your knowledge. Now let's move on to this second example, which is also something that I have borrowed from the book by Sid Sater and Hammond. And I would also suggest that because now I've already walked you through one problem. So once I set up this problem for you, you try and do this on your own first, and then see if your results match with mine. And here we're also going to bring in an interesting twist where we'll introduce an export tax and things like that. So, but let me first set up the problem for you. It's actually a pretty long word problem in the textbook, so I'm just setting it up for you with the key points that are necessary to go ahead with the solution of the problem. Now, the story goes like this. Here basically we have this cocoa shipping firm which buys cocoa from Ghana, which is basically, it's a country in West Africa. Here it's shown in red here. So this shipping firm buys cocoa from Ghana and then sells it in England, which you know is part of the United Kingdom. So basically, let's suppose this firm buys Q units from Ghana, then it will be selling these Q units in England. So that is the setup of this example, and we will start with the let me just set up the problem for you. Okay, so let's assume that the price that this cocoa shipping firm receives for the cocoa that it sells in England is is given by P equal to alpha 1 minus 1/3 times Q, where alpha 1 is positive. And because it's buying cocoa from Ghana, let's assume that the price that the firm pays per unit, per ton of cocoa is given by P equal to alpha 2 plus 1 by 6 times Q, where alpha 2 is positive. And this then gives us a total cost for the firm, this cocoa shipping firm, which would then be, because this is the per unit price that it pays for cocoa, we'll therefore multiply it with Q, because Q is the amount shipped and sold. So alpha 2 times Q plus 1/6 times Q square, that will be part of the firm's total cost. In addition, there's also a shipping cost per ton of gamma. So that would again enter into the firm's cost function as gamma times Q, and this is then our cost function for the cocoa shipping firm. Our first question is, express the cocoa shipper's profits as a function of Q, the number of tons shipped. Now, as we've seen here, the price that the shipping firm receives for cocoa is alpha 1 minus 1/3 Q, so that the total revenue for this firm by selling Q tons of cocoa is P times Q, which then becomes alpha 1 times Q minus 1/3 times Q square. And as we had already derived the expression for total cost, I've just put it down here again. Total cost for the firm is C of Q equal to alpha 2Q plus 1/6 Q square plus gamma Q. And let's just make this expression neater by collecting the Q terms. So that then gives me as the total cost alpha 2 plus gamma times the whole thing times Q plus 1/6 Q square. And now that we have the expressions for total revenue and total cost, we are in a position to calculate the firm's profits, which would then be total revenue alpha 1 Q minus 1/3 Q square minus the total cost, which is alpha 2 plus gamma, the whole thing times Q minus 1/6 times Q square. And let's just write it as a nice quadratic function. So our pi of Q, the profit function for this cocoa shipping firm, is given by minus 1 by 2 Q square, because 1/3 plus 1/6 will give us half. So that will become minus half Q square plus, just collect all the terms containing Q, that will be alpha 1 minus alpha 2 minus gamma, the whole thing times Q. The second part of the question asks you, find the profit maximizing shipment of cocoa. So we just have to maximize the expression for profits here. Now here again you can see that the coefficient of Q square is negative. So clearly this function has a max. At what point? At minus of, simply see where my cursor is pointing, here our B bar term is the coefficient of Q, which is alpha 1 minus alpha 2 minus gamma, the whole thing divided by twice the coefficient of Q square, which is minus half. So twice times minus half will give me minus 1, which will cancel out the negative sign in front of this fraction, and that then gives me the quantity shipped at the optimum, the profit maximizing shipment of cocoa, which is then alpha 1 minus alpha 2 minus gamma. And here again note that if alpha 1 minus alpha 2 minus gamma is such that it is less than or equal to 0, then the quantity chosen at the optimum will also be 0. Okay, so let's now bring in another interesting twist here, which is, let's suppose the government of Ghana imposes an export tax on cocoa of T per ton. So that is to say that if the government of Ghana imposes an export tax of T per ton, the total cost of the cocoa shipping firm is now going to go up by T times Q, assuming that this firm has to bear the entire burden of the tax. So T times Q would be the amount by which the total cost of this firm goes up. And the question now asks you, find the new expression for the shipper's profits and the new quantity shipped. So now the profits, the shipper's profits would now be given by, again total revenue expression is still the same, which is alpha 1 times Q minus 1/3 Q square. But now when you subtract total cost, you'll have this extra term in the end, which you can see here, it is minus T times Q, which you'll also have to subtract off, and that basically represents the total total amount paid as the export tax. So collecting the Q square and the Q terms, we get as the expression for profits of this firm, we get minus half times Q square plus alpha 1 minus alpha 2 minus gamma minus T, the whole thing times Q as the expression for profits. And again, you can see here that this profit function would have a max because the coefficient of Q square is negative, and the max occurs at Q double star equal to alpha 1 minus alpha 2 minus gamma minus T. So that is nothing but minus of, in the numerator you will put the this expression here, which is the coefficient of Q, and in the denominator again you will have 2 times minus half, which is minus 1. The minus signs will get cancelled, and the optimum quantity is alpha 1 minus alpha 2 minus gamma minus T. The next question now asks you, in fact this is the last part of this question, calculate the tax rate that will maximize the Ghana government's export tax revenue, which is expressed as a function of T. So basically you're being asked to help out the Ghana government to choose the optimal tax rate that will maximize its export tax revenue. But for this, we first have to find out the expression for export tax revenue, and the expression for the export tax revenue is going to be T, which is the export tax per ton, multiplied by the new shipment, which is the new quantity that is shipped post the introduction of the export tax, which is what we just found out, which is Q double star, and that will then give us as the export tax revenue T times alpha 1 minus alpha 2 minus gamma minus T, and that when you simplify gives us minus T square plus, collecting the T terms will give us alpha 1 minus alpha 2 minus gamma times T. This again, you can see here that your export tax revenue is a quadratic function of T, and again this has a max because the coefficient of T square is negative, and the max here would be at minus of B bar, which is the coefficient of T, so alpha 1 minus alpha 2 minus gamma, and that will be divided by 2 times A bar. So A bar now is minus 1, note here. So that will give you 2 in the denominator now. So our final result is that the optimal tax rate which the government of Ghana should choose to maximize its export tax revenue should be alpha 1 minus alpha 2 minus gamma, the whole thing divided by 2. So this is, with this we finish the discussion of the economic applications that I wanted to cover for quadratic functions. Let's now talk a little bit about the circle, and I have one very interesting economic application for you here as well. As you all know that the equation for the circle with center A comma B and radius R is given by x minus A the whole square plus y minus B the whole square equal to R square. And this we can further show that the equation x square plus y square plus ax plus by plus c equal to 0 represents a circle if a square plus b square is greater than 4c. So we have we'll just show that this represents a circle because this is the kind of equation which we'll be dealing with in our economic application. Now if you look at this equation, x square plus y square plus ax plus by plus c equal to 0, you can take this c, the constant c, to the right hand side to get x square plus ax plus y square plus by. I've just collected the x and the y terms, and that then becomes equal to minus c. What I've done now is I have followed the process of completing the squares, and you can see here, if you remember what I talked about in my lecture titled Quadratic Functions, to complete the squares, let's say for the x terms, what we do here is we take the coefficient of x divided by 2 and add and subtract the square of that term. So that means we'll be adding and subtracting a square by 4 to the terms containing x. And then if you collect these terms this way, you get x square plus ax plus a square by 4, which is nothing but x plus a by 2 the whole square. And this a square by 4 that you have subtracted here, you can take to the right hand side. And similarly, if you do the same exercise for y, you will get x plus a by 2 the whole square plus y plus b by 2 the whole square is equal to a square by 4 plus b square by 4 minus c. And if you do the algebra, you see that this is nothing but if you just manipulate the terms on the right hand side, the LCM is 4, and in the numerator you'll have a square plus b square minus 4c. And you can see here that this, I'm sorry, this has become a little too congested for the space that I have. So if you look at this equation where my cursor is, so we have manipulated our original equation to get something which looks like the equation of a circle, where the center is minus a by 2 comma minus b by 2, and the radius is given by the square root of this expression on the right, which is going to be half times the square root of a square plus b square minus 4 times c. And clearly you can see here that a square plus b square has to be greater than 4c to have a relevant circle, because if a square plus b square is equal to 4c, then your graph will basically be just a point, minus a by 2 comma minus b by 2. And if a square plus b square is less than 4c, then you can see here the expression under the number under the square root sign will become negative, and in that sense you would not have any real any circle in real space or any real radius. So for a meaningful circle in real space, you have to have a square plus b square greater than 4c. Okay, with this, let me now set up the economic application for you. So here we have a firm which has two plants, A and B. Plant A is located at this point 0, 0, where my cursor is right now, and plant B is located at 60, 0, which is basically to say that these two plants are 60 kilometers apart. This represents the distance between the two plants, or you could just call them firms, because actually they are just firms. So as I was saying, this firm has two plants, A and B, and there is a shipping cost also which the firm has to incur in order to ship the good to where you're located. So the shipping cost per kilometer from A is, per kilometer per unit from A is rupees 10, and from B the shipping cost is rupees 5. Okay, so let's suppose there's an arbitrary purchaser or a customer who's located at a point like x comma y. Then we can see here that if this arbitrary purchaser, if he decides to purchase from plant A, then he's going to end up paying the price P, which is the price of the product itself, plus he also has to pay for the shipping cost, which is going to be 10 times the distance between plant A and the location where this customer is located. So that's going to be, if the customer decides to buy from plant A, he'll have to pay a total price of P plus 10 times square root of x square plus y square, right? Because that's a distance, square root of x square plus y square is a distance between x comma y, where the customer is located, and the point 0, 0. Similarly, if the customer decides to buy from B, then he's going to end up paying a total of P plus the shipping cost, which is 5 times the distance between where the customer is located and plant B, and that distance is square root of x minus 60 the whole square plus y square. So this is to give you a general sense of things. Now let's look at our question. The question here asks us, find the equation of the curve that separates the markets of the two firms. Now, first of all, you have to understand here what we mean by the equation of the curve that separates the markets of the two firms. Note here, or if you note here, the customer has a choice of two firms. He can go either to firm A or firm B, and clearly I think all of you would agree here, he would buy from that firm that charges a lower price, or he will buy from that firm that from where he can obtain the product at a lower cost. So that is something natural, and that then actually helps us highlight three kinds of locations. So in this context, we can talk of three kinds of locations. One set of locations in this space that you see here, this two-dimensional space that you see here in this slide, one set of locations would be such where that the customer will go only to firm A because he is able to obtain the product from firm A at a lower cost. then there will be some other set of locations such that the customer would only buy from firm B because he is able to obtain the product at a lower cost when he buys from firm B. So just to give you a general sense of things, if let's say if I go to firm A and I have to pay a total of rupees 100, but if I go to firm B and I have to pay a total of rupees 50, then clearly I will go to firm B because firm B is charging me a lower price in totality. This is the price P plus the shipping cost. So in that sense, we can talk of three types of locations. One set of locations where the customer will just go to plant A, another set of locations where the customer will just go to plant B, and then there will be a third set of locations where we can say that on all these points, the customer will be indifferent between buying from firm A and buying from firm B. So if for example, both the firms are charging the same price for the product after the inclusion of the shipping cost, then clearly the customer is going to be indifferent between the two plants. Now, that set of points where the customer is indifferent between buying from the two plants, that then gives us the equation of the curve that separates the markets of the two firms, because then we'll just see in a bit that once we find all the points where the customer is indifferent between buying from A and buying from B, there'll be one region that will be demarcated where the customer will only go to firm A, and there'll be another region where the customer will only go to firm B. So, and these regions will be on either side of the set of points where the customer is indifferent. So, let's first find out where the what will be the set of points where the customer is indifferent between buying from A and buying from B. That will be the case when he ends up paying the same amount to firm A and to firm B in totality. So, how much when the customer buys from firm A, we saw that he was paying P plus 10 times square root of x square plus y square. So, we equate that to P plus 5 times square root of x minus 60 the whole square plus y square. And if we do the algebra for this equation, we will see here that the P terms get cancelled on both sides, and basically this equation boils down to 2 times square root of x square plus y square equal to square root of x minus 60 the whole square plus y square. So, this would then give us a set of points where the customer is indifferent between buying from A and buying from B. Basically, twice of the distance between the customer's location and plant A has to be equal to the distance between the customer's location and plant B. And we can simplify this further. If I square both sides, I get 4 times x square plus y square is equal to x minus 60 the whole square plus y square. And again, let's just open up the brackets. We'll get 4x square plus 4y square is equal to x minus 60 the whole square gives us x square plus 3600 minus 120 times x plus y square. And this you can now you can collect the terms for x square, y square, x, y and so on. So, that will then give you the equation 3x square plus 3y square plus 120x minus 3600 equal to 0. This here in this equation, I can now take 3 common because that will come out common from all these terms on the left. So, that will then give me my equation x square plus y square plus 40x minus 1200 equal to 0. This is going to then give me the set of points where the customer is indifferent between buying from A and buying from B, and this then is the equation of the curve that separates the markets of the two firms. In particular, please notice here that this is nothing but the equation of a circle with center equal to, if you remember the formula, I've also put the formula down below on this slide. The center is given by minus of the coefficient of x divided by 2, so that will be minus 40 divided by 2, comma, minus the coefficient of y, but the coefficient, there's no y term here, so that will be 0. So, this is basically the equation of a circle with center minus 20 comma 0, and the radius here is going to be half under root a square, which is basically the coefficient of x squared. So that's 1600 plus b, if I use the formula, b square is 0 here, minus 4c, which will then give me minus 4 times minus 1200, which is 4800, and that then gives me the radius, which is half times 80, which is 40. So that then gives me the equation of the basically it's a circle, which will then give me the equation where which will then give me the curve that separates the markets of the two firms. And alternatively, I can express the circle as x plus 20 the whole square, because the center is at minus 20 comma 0. So this is written as x plus 20 the whole square plus y square equal to 40 square. 40 is the radius. So this you can see here, I've given you a visual here. The circle is the set of all points where the customer is going to be indifferent between buying from A and buying from B. And intuitively you can see, if you are going to be located inside the circle, then clearly you would want to go to firm A. You can see visually that firm A looks like it's closer, but if you're outside the circle, you're going to go to firm B. And this we can quickly verify that you're inside the circle if you're buying from A. You can just take the total price that you pay if you're buying from A and put that less than the total price that you pay if you're buying from B, and you see that you'll get the equation x square plus y square plus 40 times x minus 1200 less than 0, and that is clearly the case where you're inside the circle. So whenever you're inside the circle in this yellow shaded region, you're going to be going to firm A, and you can now see that the circle is very nicely demarcating two regions. One region, this yellow shaded region, where the customer will exclusively only buy from firm A, and the second region is this region in blue outside the circle, where the customer will only go to firm B. And just as a quick point to think about, you can think of something like this. So you might ask, well, if the customer is located at minus 70 comma 0, which is outside the circle, wouldn't it be easier for him to just buy from firm A? No, that does not work, because if you notice here, if let's say the customer is located at minus 70 comma 0, now remember he pays the same price P for the product. The only difference is in terms of the shipping cost. Now if he buys from firm A, the shipping cost that he will pay will be how much? That will be 70 times 10, because 10 is the shipping cost per kilometer and 70 is the distance between the customer located at minus 70 and A. So that will be 700. But if he goes to firm B, remember that going to firm B is actually the shipping cost is less. So here if you notice, the distance between minus 70 and 60 is 130, and 130 times 5 is 650. So that is clearly a lower price that the customer will have if he buys from firm B. So clearly outside the circle, the customer is better off buying from firm B. And with this, we come to the end of today's lecture. I've completely run out of time. The next lecture will be on cubic functions, and until then, goodbye and take care.